We had discrete. uh, We had discrete. Remember discrete? Just to help some of you out, because some people had trouble with this on the exam. Discrete means something that you can count. 0, 1, 2, 3, 4, so on and so on. At the start of chapter 4, we also talked about continuous random variables, which means that you could have anything. So you could have 0, you could have 0.36, you could have 2.8. Those could be your variables, your x's. Well, all of chapter 4 dealt with the discrete part, and now this chapter is going to deal with the continuous part. So we're finding probabilities of those continuous random variables, and what that means is we're going to deal with the normal distributions, and probably Dalton can relate that back to what we did back in like chapter 2 and chapter 3. When we say normal distributions, we're probably talking about what? Your normal curve. All right. So instead of what we did in chapter 4, we made histograms for some of the stuff, and it might have looked like this. And we found the probability of, we found the probability of getting something in that little part right there or whatever. Well, now we're going to find the probability of getting it, but we're going to use this area. And I know it probably wasn't completely and totally fair, but there was a problem on the exam where it said on your normal curve, because we hadn't really completely talked about this, if your mean is 50, or no, it didn't say the mean was 50, it just said what is the area below the curve from the mean down. Well, what's the area going to be there? 50%. And that's a lot of what we're going to do here. So in this chapter. So we're going to deal with, and not only is that 50%, but if we're trying to find, let's say, Jacob's score is in that. Jacob, your score will never be in the lower 50%, right? It's always in the upper, but just deal with me for this time. If Jacob's score is in that, then there's a 50%, or there's a 50% chance, a 50% probability that his score is in that. And that's what we're going to do. We're going to find probabilities. Maybe we want to find the probability that Grant scores in that little area. Well, we're not going to have all the scores, and we're not going to have all the different things that could happen, because now it's continuous instead of discrete. So what we have to do is just look at that area, and that area will be our probability. So if this little area right here is 0.13 of the entire area, then that means there's a 13% chance that Grant's score falls in that area. That's what we're going to do. So the first part of this is interpreting graphs of normal probability distributions and finding the areas under a standard normal curve, which we've talked about. Again, the standard normal curve looks like this. When we dealt with the empirical rule, looks something like that. You're going to have to be able to draw these. Now, every time I draw the standard normal curve, mine looks like that. It doesn't have to look like that. It very well could look like that. All right? All that makes it standard normal is the fact that the mean is here and it fits that empirical rule as we go out from the mean. So there's, what do we say, 34% here, 34% here. It's like 13.5% here, 13.5% here, so on, and that's something we'll cover. And this is like 2.5 or something, is that right? 2.5. And once we get out to here, remember, if you're outside those two standard deviations away, what do we know about the scores out this way? They're considered what? Can't read that writing, huh? Unusual. Anything out here, anything, oops, I didn't go over far enough here. Anything out here is considered unusual. When you get out in here, once you're out past 3 standard deviations away from the mean, then you're considered very unusual. All right, so anything that would be out here, out here is where Jesse would score, right, Jesse? This would be you out here. And he'd be way out there, so he'd be very unusual, and he'd be like an outlier. That's why when I graded the exams and everything, I graded Jesse's and then I curved everybody else's, but Jesse's I had to take out of the curve because he would have screwed it up for everybody. So he was that one that was way out there. Put that away and write stuff down. Yeah, I know you don't need any notes, because we talked about your grade being up there. And no, you did not get a 94, don't let him lie to
That's
you.
what it says. He knows. That's what it says.
Might have been backwards. Were you dyslexic? Did you read the numbers backwards?
Instead of a 94, I got a 6.
All right, a continuous random variable. We talked about a continuous, again, discrete, something you can count, continuous, something like hours spent studying a day. Well, instead of just being, okay, you have to spend a solid 1 hour or 2 hours or 3 hours, you could spend an hour and 10 minutes, an hour and 6 minutes, an hour and 2 minutes, whatever. So it's a continuous. So we use this number line where you have, it contains all of it instead of just having the dots on the solid numbers like what we were doing with discrete before. So continuous random variable, infinite number of possible values that can be represented by an interval on the number line, not just dots on the number line. Again, some things, because if you take a test, you're going to get a 94%. Or whatever, unless your name is Jesse, then we know it's not that.
Do you want me to show you?
If it says, I better check it
It says 94.
on your exam.
Semester 1 exam, 94%.
That's what it said. You showed us.
You want to see it?
Man, I'll figure it out.
If you had an 80, what's wrong with me getting a 94? That's like.
I just know you didn't. So, if you get a 94, does that mean, even if Jesse's is wrong, does that mean he got exactly a 94? No, he probably got like a 93 point something or something like that, and that's what makes it continuous, even though we don't look at it in that fashion. Continuous probability distribution is probability distribution of a continuous random variable. That's the same thing we've been doing, except now continuous instead of just discrete. So nothing really new here, it's just going from discrete to continuous. Normal distribution is a continuous probability distribution for a random variable x. Same thing, instead of a discrete probability distribution, we're dealing with normal distribution. The most important continuous probability distribution in statistics, this is the one that we use the most, in other words. A lot of the stuff that we do, and this goes back to what we talked about at the very start of the year, when we talked about the different types of statistics, where you have what the insurance company does, which is they sort of are subjective and they say, well, we expect that a 16-year-old kid's going to have more accidents than a 25-year-old person. And that's sort of what we're doing here. It's not going to be something that we can do exactly, but we're going to be able to get close. The graph of a normal distribution is called the normal curve. Looks like that. We've dealt with the normal curve several times. You'll also have to remember when you're dealing with the normal curve, remember the empirical rule that we talked about earlier in the year. What's the dotted line down the middle of this curve represent? That's the mean. So your mean's always going to go there. We'll hit this one, see if it, yeah, it's on the next one. Let's go back. So mean's always going to go there. And you're going to have it separated. This is one standard deviation below the mean, one standard deviation above the mean, a second one, or number 2 below the mean, number 2 above, number 3 below, number 3 above. And with the empirical rule, we had all the percentages about how they should fall in there. And again, this normal distribution doesn't have to look this way. It could look more flattened out, but you're still going to have your mean in the middle, so on and so on. It could look more straight up and down like that. And all that's telling you, and we'll go through it as we go through some more PowerPoints. Here you have your mean here, right down the middle, and your standard deviation is to each one of those lines. Here you have your mean. Well, when you do your standard deviation, apparently on a graph like this, is your standard deviation bigger or smaller than this standard deviation? Would the standard deviation be the same? Be smaller, wouldn't it? All right? So when you have that big steep hill, that means you're less spread out. Your standard deviation tells you how far you're spread out. If you had something like this, your standard deviation would be more spread out. Or your standard deviation is bigger, which makes your graph more spread out. Your mean on all of these, your mean could be exactly the same thing. Maybe the mean on this one's 20, the mean on that one's 20, the mean on that one's 20. All the means could be exactly the same, but then your standard deviation is telling you how your graph is actually spread. Mean, median, and mode on a normal distribution will always be exactly the same. They're always equal, so the mean, median, and mode always right there, they're always the same. These are properties of a normal distribution. Normal curve is bell-shaped and is symmetric. What's symmetric mean again? What's that tell you about the two sides? They're the same. Same on both sides. It's always going to be symmetric. So even if it is drawn different, even if it's a taller hill, it's still going to be symmetric. If it's a more spread out hill, it's still going to be symmetric. The total area under the normal curve is 1. This is where I sort of started to explain this a few minutes ago, where I sort of cheated you on the exam, hoping that you just know it. the whole area under the whole curve is 1. So what's the area under from the mean down that way? Half, 0.5, 50%. The normal curve approaches but never ever touches the x-axis, so it never touches your x here. When you were in Algebra 2 or Pre-Calc or any of those other math classes, you talked about when you had a graph, and the graph might have looked something like this, and it came down like this, and then went to here, but it never ever completely got to that line. Does anybody remember what those were called? What they called asymptotes or something like that? Sort of the same idea here, a little different, but sort of the same idea. So the farther out we go here, the closer and closer and closer it gets to the x-axis, but it's never ever actually going to touch it. What if I was right about here? What if this was my x that I'm looking at? What would we expect the area to be from there to the left? Make a guess. What percentage of all the scores are going to fall from that mark to the left? 65% maybe? How about if we were right about here? There to the left, how much would we expect? More than that, 90-some percent maybe. And this is what you're going to have to do. What we're going to do is we're going to be looking at these normal curves, and they're going to say, okay, if you're right here, what's the probability that somebody's score falls from there down? Well, if you use your brain a little bit and just think about it and draw it out, you can probably get a pretty accurate guesstimate, okay? So you could probably guess and say, okay, from here over, maybe 80%. If we're looking at this normal curve and we're saying, what's the chances that somebody's score falls in there? You know, you might be thinking about 10%, maybe 15, but somewhere in that area, not 50, right? You know, it's got to be less than 50. So you should be able to get some idea. Now the paper that I passed out, it's got z-scores on it, and these are actually the percentages and the area that's under. But the first thing we got to be able to do is change into a z-score. I know Michael remembers exactly how to change everything into a z-score, right?
I know I forgot everything.
All right, the fifth thing, these inflection points, I'm going to tell you how to find the inflection points. The inflection points are where the first standard deviation is. One standard deviation above, one standard deviation below. I really wouldn't write all this down because it's telling you that the curve changes directions as it gets to those inflection points. We're not going to deal with that a whole lot. The main thing here on this fifth thing is know that the inflection points, one standard deviation above and one standard deviation below. So when we get to that first standard deviation above and below, those points are called your inflection points. That's where the curve changes the direction it's going. All right? So the part that's really important here is just the inflection point part. And maybe draw that graph and know that at that point and at this point, those are called the inflection points. Again, on all this, what's mu stand for? The mean, good. And what's sigma stand for?
Standard deviation.
Standard deviation.
I got it 94.
That'll be changed today.
You better not change that.
That
I already showed my parents. They're
You
already-
did not, you didn't even know it was there
Yes,
till
I
a few
showed
minutes
last
ago.
night. When we were
I
out
don't
to
believe
eat.
I screwed that up.
You didn't screw it up.
Yeah, I did.
No, you didn't. I got a good, pretty grade. I knew I did good. As soon as I handed that test in.
See, he's just gonna keep it up until I blurt out his grade, and
Blurt it out, I wanna hear it. 94. It's a 94.
and then you woke up. Alright, inflection points.
You can't change it since you already put it on.
Yes, I can.
No, you can't. I'm gonna screenshot it, so.
The inflection points can be estimated and are located at one standard deviation above, one standard deviation below. Mu is the mean again. Sigma is the standard deviation. We just got done talking about all that. Again, remember, you're looking at that curve, how it's split up there.
You better not. I know it does. You know, I'm still gonna believe I got a 94, no matter what.
Might be helpful here, because I don't know if I put this anywhere on the slideshow. Somebody help me out. I know this is 34%, right?
Yeah, so is the other side.
Okay, I got it. Not a 94.
What was, hey, I've been saying that the whole time. What was this one? This is 13 and a half, is that right?
That would be 13.5.
Is it 13.5, 13 and a half? Might want to write this down somewhere. It will be helpful as we go throughout this chapter to make sure you remember this, because some of the times they're just going to say, what percentage of the people or what percentage of the grades fall between one standard deviation below and one standard deviation above? And then you could just write down 68%, or 0.68 would be the probability. And what did we say this one was, like 2.5?
Yeah.
It's actually like 2.3 or something like that, and then the other parts are out.
Yeah.
It's like 2.3% and 2.3%. And then the other, because this should all add up to 1, the other 0.2% or 0.4% are the outliers. So anything that's out here, the other thing, remember, if anything from here down is considered unusual. Here up is considered, sorry, right here, 1, 2, I know we're at 3 out here. That's wrong spot. Here down is considered unusual. And here up is considered unusual. Then once you get out past the 3 standard deviations, which is way out here, if you're outside of that, it's considered very unusual. Don't let this confuse you. This looks confusing at the bottom. This is your mean plus 1 standard deviation, your mean plus 2 standard deviations, mean plus 3 standard deviations. We had one of those problems on the exam. I asked you, it said that the mean was 50 and your standard deviation was 10. and you had to draw the normal curve for it. Not a very good drawing. So you put 50 right there in the middle. One mark here, go down one standard deviation, that'd be 40. You go down the second standard deviation, that'd be at 30. Go down the third standard deviation, that'd be at 20. Go up one standard deviation, 60. Second, 70. Third standard deviation is 80. So be able to draw, you gotta be able to draw these curves. Main thing for this whole chapter, you'll see me drawing that curve over and over and over and over and over again. Sean's not gonna be able to do any of this if he can't draw the curve and look at it, all right? I know he thinks he can. Mr. Eversole's just an idiot. He's gotta see it visually, but it might be really, really helpful if you draw the curve. All right, probability density function. Like a histogram for discrete probability distributions. So it's sort of the same thing. What we're doing is figuring out what part falls in that certain range. PDF is the abbreviation, same on the calculator. That's where the PDF on the calculator comes from that we've been using. Now this formula, we're probably going to use the calculator for most of this, but I can't remember for sure if we ever use that formula or not. We might. But on this formula, got to know your sigma, got to know your x and your mu. Your x is the number you're looking at, your mu is your mean. Then you got sigma squared. Sigma squared is your variance, which is, you can still use the sigma in there. Sort of hard to punch into the calculator when you do use this formula. Does anybody remember what this is? Pi, what's it stand for? 3.14 something, 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 right? Does anybody remember what this is? E, but what is it?
It's a fixed number like pi, but.
It's a fixed number like pi. Grab your calculator, and I bet your calculator's got an E button on it. And if you punch the E button, it'll tell us what it is. Big calculators might just say E.
2.71828182.8.
Say it again.
2.71828182.8.
So both those numbers are actually fixed, and both of them are on your calculator somewhere. So you can just put those in where they need to be. The ones that you're going to have to actually know for the problem is your sigma, your x value, and your mean, your mu. So what this probability density function is, when we were doing histograms, maybe our histogram looked like this, and they ask, what's the probability that Johnny's score was at or below that? And then we just added up those three columns and put that over top of the total. Well, now what they're saying is, what's the probability that Johnny scores at or below this, and we're on this normal curve? Well, then what we're actually finding is that area right there. And that's the formula to find that area. All right, normal curves depends on the mean standard deviation. We just talked about this. Pi is 3.14, E is 2.718. Mu gives the line of symmetry, the mean is the line of symmetry. So when we're looking at that normal curve, that's the line of symmetry. So if we were to fold this, the two sides should match up exactly. And the sigma tells how much the data is spread out. So again, sometimes you'll have a normal curve that might look like that, where the data sort of all close together. Sometimes you'll have a normal curve where it's more spread out. Other times it may be really spread out, and it'll be a real low curve. And the standard deviation, the sigma, tells you how that's going to look. If the standard deviation is small, then it's going to be a steeper normal curve. If the standard deviation is big, then it's going to be a more flat normal curve. Now the bad thing with this, when I draw a normal curve, I'm going to draw that one just about every time. All right, so even if it's supposed to be steeper or more spread out, mine's going to look that way 99% of the time. Means and standard deviation normal distribution can have any mean and any positive standard deviation. Standard deviation always has to be a positive number. You can't have a negative standard deviation. Unless you're dealing with Jesse's test scores, then we go into the negatives.
I got an 87.
Shania, how come you got that look like you don't believe him?
Just
The mean gives the location of the line of symmetry. Standard deviation describes the spread of the data, how it's spread out. So these are the different ways that it could look. We look at all this. What's the mean of this first one?
3.5.
What's the mean of this one?
3.5.
They're the same mean. How come they look completely different?
One's bigger.
Inflection.
How come they look different?
Standard
Standard deviation. This one's got a bigger standard deviation. Looks like standard deviation is more than 1. This one's got a smaller standard deviation, so it's clumping the data together more. Right? So bigger standard deviation, smaller standard deviation. What do you notice on these two?
They're the same.
Are they the same?
Except for the means.
The means are different, aren't they? So the standard deviations are the same on those two, but the means are in different locations. All right? So if you change the mean, the curve's still going to look the same, but it's going to be like slid one way or the other. If you change the standard deviation, it's going to change how steep the curve is. That's what it tells us down there. Notice that on these two, the standard deviations were 0.7 each. On these two, the means were the same, but the standard deviations were different. On this, which curve, A or B, has the greater mean? A. How do you know A's got the bigger mean? Because it's farther to the right. The mean would be right in there, right? Looks like the mean's probably 15 on that one. What's the mean look like on the other one? Probably about 12. Which one's going to have the bigger standard deviation? B would, because it's more spread out. We just said that. B has a bigger standard deviation. On these three, which one has the largest mean? C. Which one has the largest standard deviation? B, because it's flatter. Line of symmetry. Where would the line of symmetry be on A? About what?
12.3.
12.3 maybe? Where would it be at on B? About 13, somewhere a little more maybe. Line of symmetry, just be straight down through there. And that line of symmetry is also your what? That's your mean. Scale test scores from New York State grade 8 mathematics test are normally distributed. The normal curve shown below represents this distribution. What is the mean test score? Estimate the standard deviation. What do you think the mean test score would be here? You gotta be able to read stuff like this. If I drew a line down through here, is it gonna help a little bit?
660. 675 maybe? Cause your line's a little at an angle, but it looks like 675.
What are we going by?
It's 680.
What's this right there stand for?
Yeah, 60.
660,
680.
680 maybe?
Right.
All right. Line's a little slanted, it might be 675, somewhere around there though, and that's why I said estimate it. Estimate the standard deviation. How can we figure that out?
Right at the numbers right there. Like right at 650 and.
You think, so you think the first standard deviation's there maybe?
Yeah.
Yeah, maybe, let's try it and see. What is that standard deviation? How many over?
30.
30. So we need to go 30 this way, right? So that'd be right about there. Then we go 30 more for the next one. 30 more, 10, 20, 30. 30 more, 10, 20, 30. 10, 20, 30. Does that make sense for it to be split up that way?
That's good.
That looks pretty good. So maybe the standard deviation is about 30. So 675, so Nick back here had to be exactly right. Don't even start off the year that way, Nick. All cocky and stuff. Standard deviation that says about 35, we said about 30. All right, how to graph these normal curves on a calculator. You might want to write this down. This is going to tell you how to graph on a calculator. I don't have this listed out on the paper anywhere this time. So Grant's going to have to make sure that he keeps this because I don't have it printed off or anything for you. If we wanted to graph on the calculator, we wanted to actually graph these normal curves. Bad thing with doing this, and I hate to do this on my calculator because it seems like when you graph these on your calculator, and you probably did some of this when you were in Mr. A's class on the calculators, once you graph something, then it screws everything else up, so you gotta go back in and fix your setup. That's the way this is. I think we did, earlier in the year, we also did the scatter plots. Did we do the scatter plots on the graph, on the calculator? We didn't do them yet. That might be something we're gonna do. Maybe I'm ahead of myself. But it sort of messes up the calculator. Doesn't mess it up, just you gotta go back in and reset your table and all that stuff. So you go to the Y button, which is your graph button right there under the screen. Second bars.
Challenge some cereal, watching some TV.
You would be doing that, I think.
Yeah, on a day off. But no, we're here. I know. I would.
Under bars, you want the number one, which is, what is it? What's it called? Is it just the one variable, whatever it is? Normal PDF. So you want the normal PDF. Then the things you're gonna have to punch in. You gotta punch in your X, that's the number where you wanna be, comma, the mean of the data you're dealing with, comma, then the standard deviation, close the parenthesis, hit graph, and it'll show you the normal graph. So if we were to take that one that we just had, we said that, what was it, 675, was that the,
Yeah.
was that the mean? 675 was the mean. Let's say we want our X to be 500. Nah, we don't want it to be that low, that's gonna be, so we're off the chart. Let's go with 600. And our standard deviation was 35, we punched that in. On your calculator, it should actually show you the graph.
Not the calculator in the car. I don't remember these chairs were sucking so bad.
All you have to make sure too that you have this, have all your stuff cleared on your graphs. So you go to the Y button, second vars, not tangent, stupid. Second vars, normal PDF. So that means we want the normal curve. Then you punch in your three numbers, 600, comma, 675, comma, 35, close the parenthesis, hit graph. Now Michael looks at it, you see my graph? He doesn't see it, does he? Because what? What's wrong with our numbers? We're pretty big, right?
Yeah.
So we're gonna have to adjust the screen
I hate that.
to fit that, and that's what I was saying, this, why usually I don't do it. Usually I would just take my pen and I do this, draw this, 675, goes right there, put some marks on here, put some marks here, and subtract 35 going down, add 35 going up, and draw the graph that way instead of using the calculator, because as soon as you start changing your table and everything on here, as soon as you start zooming in or out, then it's screwed up until you fix it again, and you gotta change it every time. I'll try those. Alright, this is very, very important. Standard normal distribution. So that Dalton probably wants to come back to this planet. Maybe jot some of this down. You know, I've been nice all year and it's about done. So, like, a lot of the times when I let you use your binder and stuff on the test, probably not gonna happen. Write it on hand.
I write everything.
Makes all normal curves look the same, uses the mean as 0, uses standard deviation as 1. Z-scores are on the horizontal axis, so this is changing everything into something where we can compare them all. And just like on the calculator, not have to change our scale. So if we wanted to compare your history exam scores to your math exam scores, we could change them all into one standard score, which is a Z-score. Your X value, like that 675 that we were just talking about, that's called a raw score. So anything that's like the actual score is called a raw score. When we change it to the standard normal distribution, we're dealing with a z-score. We dealt with z-scores earlier this year. Remember, you take the value, whatever it is, x, minus the mu, divided by the standard deviation, and that changes it from that 675 into a z-score. Where our normal curve, instead of our normal curve looking like this and having right here in the middle having 675, now this middle is always going to be 0. This might be a good idea. I can't remember if on the next slide I have this or not, but it's, your normal curve, your standard normal distribution is always going to look like this. This is your mean, and then each one of these spaces counts as one standard deviation, above or below. And we change everything to that one picture so that we can look at them all the same instead of looking at a million different kinds of graphs. So this is what your standard normal distribution is going to look like every single time. Now, to look at this, we have to change all the scores into z-scores to put it on there. All right? The 0 here would match up to our 675 on the other one. Each one of these spaces would match up to the 35 on the other one. And then we could take that 600 and stick it in right here for x, minus 675. Divided by 35, do all that, and we could figure out where it's going to fall at on this. Let's see, 75, that'd be about negative 75 divided by 35 is negative 2 point something. So it's going to fall, that score would fall somewhere about in there. And we can look at it that way and say, okay, that's where that person scored, that's 600, that's where it fell. Normal distribution with a mean of 0 and standard deviation of 1. Remember, the area is always one whole. Any x value can be transformed. You change it into the z-score. That's what we were just talking about. If each data value of a normally distributed random variable x is transformed into z-score, the result will always result in a standard normal distribution. So even when, what this is saying, even when you have some curve that maybe isn't normal, if we change all these into z-scores, we can make it into a normal curve. Okay? And then we can compare everything. Here all it's doing, saying, all right, if we go from just a normal distribution to a standard normal distribution, we're changing everything from just raw scores, 600, 675, 625, 580, whatever all the test scores were, we're changing them all into z-scores, where it's going to be like 1.3, 2.6, negative 3.8, thinking about Jesse's exam score there. Would negative 3.8 be a good z-score, Jesse?
Well,
That would be like way down here somewhere, right?
probably like 8.2,
8 points.
somewhere around there.
We can use that table that I gave you, we can use that once we've changed them all into z-scores. Now we can use that to find the area. We can find the area from some score and below it. And we're going to talk about that here in a second. Formula for PDF, that's what we wrote down a few minutes ago. For the standard normal curve, this is the formula. A little easier. So you've already got this down, this is the new formula. For standard normal distribution, instead of have to do all that extra stuff, it simplifies it down quite a bit. Again, even though it simplifies it down a little bit, does that still look like a formula you want to deal with? Probably not. Yeah, you write down everything.
I do, but I don't know why I'm tired.
I'm not writing that formula down right there, because you probably got it memorized already, that's why.
The 94 and everything,
Y equals 1 over this.
This one here is the one that we're writing, we already wrote the other one.
Well, I got the PDF memorized.
All right, properties. Properties of standard normal distribution, cumulative areas close to 0 for z-scores close to negative 3.49. What that's saying, if we get down here to like 3.5, anything to the left is basically going to be nothing, 0. All right? All the time that we're talking about this, we're talking about stuff to the left. Areas to the left. Cumulative area increases as you go farther to the right. So in other words, if I come over here, now we're talking about this area. If I want to come over to here, now we're talking about all the area from there to the left. If I come to here, now we're talking about all that area. And if we're talking about all the area below 0, what percent of the area are we dealing with? 50% of it. All right? If I go to here, now we're talking about all the area from 1 standard deviation above the mean down. So we're always going to the left. And that's what this chart does. This chart tells you the area from that z-score to the left. Cumulative area of z equals 0 is 5, is half of it. We just talked about that. If we're way up here, what do we expect that this area is going to be now? Should be close to 1 whole, 100%, 1 whole. So 3.49 above and down, that should be everything. Negative 3.49 and below should be nothing. There shouldn't be anything down that far. We're looking for a particular z-score. This is sort of like on the test, I had on there the percentile. Oops. Had the person in the 90th percentile. What's being in the 90th percentile tell you? Maybe. You got partial credit if you said that they had a good score. That's not all it tells you. What's that tell you? They did better than 90% of the people. Well, when we're looking here, sort of the same thing. We know that we're looking at this area. This person, if their score is right there, then they scored higher than whatever this percentage is of the area down this way.
So that'd probably put me in the 90th percentile, wouldn't it, for the exam?
Sorry, the graph didn't go over far enough. All right, on the table, that's that table there. This is what I ran off for you. if you're not on the table, if the number that you're looking for is not on the table, like you're looking for a z-score of 2.15 and it's not on there, get as close as you possibly can. Okay? 2.15 is on here, but we'll talk about that here in a second. So looking at this table, to find the area. We want to find the cumulative area that corresponds to a z-score of 1.15. So we'll give Jesse some credit this time. We'll say that his z-score on our exam was 1.15. Does that put him above average or below average? If his z-score was 1.15.
Above.
Above, all right? And you got to remember, if we're in the positive, that right there is your mean, that's 0. Then you're going to have 1, 2, 3, -1, -2, -3. If you're in the positive, you're above the mean. If you're in the negatives, you're below the mean. So if he's at 1.15, the way you use this chart, go on your z-score, down this first column, and you go down to 1.1. Then if you look at the top, along the top, it goes out an extra space. So we want 1.1, and then we're going to go up here to the 0.05. And we go down, we match those two up, and what's it tell you? Yes, it was. What's it tell you? 0.8749. So what we're saying there is if Jesse's z-score was 1.15, what percent of the people did he score higher than?
87.
About 87% of the people he scored higher than. So he would be right in here, and what we're saying is the area of all this stuff underneath here, it has an area of 0.8749. It's about 87% of all the area. Almost 88% of all the area. Almost 87.5. Does that make any sense? Michael, will that make any sense? So we look down the first column, go to 1.1, go across, 0.05, look right there. That's telling us that that's the area to the left. All of these tell you areas to the left. So what's the area to the left of 0.01? A little more than 50. 0.5040, right? It's telling you the area to the left on our standard normal curve. Negative 0.24. Notice on this side, no negatives, but if you flip over on the back, it's got the negatives. So you go negative, we want 0.24, so we go down to negative 0.2, and you go over to the 4. What's that tell you about the area? About 40%. Where am I going to be at on here if we're at negative 0.24 z-score? Am I going to be like way over here?
Below the.
Going to be below the mean, right? Way below, like way down here? No, negative 0.24 is going to be somewhere real close in there. So we're looking at this, and the area to the left, we're saying is about, what did it say, 0.4,
0, 2, or 9, 0,
sorry,
5, 2.
0.4052. So about a little less than 41% of the data falls on that side. So we go down to negative 0.2, over to the 0.04. We're right there. That's how we use this chart. Now, instead of using the chart, you can use your calculator. So write this down. This is how you use the calculator to find that same stuff. Talking to the floor. No, I was talking to the floor. To use your calculator to find the area find the area to the left. No, it's going to be screwed up on there. All right, Shania, give me a Z-score.
3.4.
So she's going by her score, not Jesse's, right? 3.4.
I got 6.7.
We already talked about what happens when you get up past 3.49. It's nothing.
It's above.
There's nothing there. If we take our calculator, hit second, bars, this time we want number 2, which is normal CDF, not the normal PDF. Hit enter, and then what we're going to punch in. And again, what this is doing, and we should know, we're looking at this normal curve, and we're finding the area that's below or to the left of this Z-score. Well, Shania picked 3.4. What should our calculator tell us is the area below 3.4? Should be awful close to what? 100. Should be real close to 1. All right, 100%. We punch in. When you punch this in, we're going to punch in negative 10,000. And the reason we're going to punch in negative 10,000 is because we just want it to go out that way as far as it can possibly go. I think the book says punch in negative 10. So you really don't have to punch in negative 10,000. That's just a big number I made up because we want everything out this way.
Mine had negative 1 to the of 90, or E99 over there.
When you did all this.
No, I just opened it.
Mhm.
It comes up negative 1 E99.
Let me do it and see. So if we punch in negative 10,000, again, I don't think you have to punch in 10,000. That's just giving us the low limit. You could punch in just like negative 5 or negative 10 or something probably, and it's going to get you down there far enough to make sure you got everything. Hit comma. Our Z-score is 3.4. Close the parenthesis. Hit enter. And it says that. Is that pretty close to 1 hole? Yeah, it's 0.9996630. So that means that her Z-score would be higher than about 99.97% of all the scores.
Come here for a second.
Mine's different, but
yours different?
Mine is too.
The new ones?
Yeah. Second on top, this is a lower.
Oh, okay, so just punch in on the lower, punch in this, then what's it got, upper limit?
Yeah.
Then punch in the 3.4, that's your score.
View.
It wants mu, 0,
And standard
Standard
deviation.
deviation. 1.
1. Cause we're on our normal standard, does it say 0.99966? Okay. So if you're on the new one, what you want, and the new one's probably easier because sometimes we're gonna want to go from like this score to this score and we wanna find that area. Well then, it's just asking you the high limit and the low limit and you just punch in those two numbers. For ours, for the other calculators, a little more difficult. Alright, when you're doing this, when you're finding these areas, sketch, you gotta draw this, you gotta sketch the normal curve. Jesse, you've seen me draw this normal curve about 600 times already today, right? You've got to draw it so that you're thinking about it. So that way I know if my z-score is 2.8, I'm over here somewhere. Well, right away I know that my final answer, if I come up with a final answer that's 0.4063, what do I know about that answer? That's wrong, because that z-score of 2.8 better be more than 0.5, right? It's got to be higher than that. So you can sort of get some idea of where you're at. So sketch it, that way you know where you're at. Find the area. Different cases that we're going to have. If we're just looking at the area to the left, then you're just going to find this. And we can just use the calculator like we just did there, or just use the table. If we're looking at area to the right, then what we want to do is take this number and we can punch it into the calculator. And what we would actually be finding is the yellow area here. But we don't want the yellow area. We want the blue area. So what we'd have to do is take this answer that we got and subtract it from 1. So 1 minus that. And that would give us the blue area. Does that make any sense? Not really. It does. So what we do, let's say we wanted to find this 1.23, we punch it in on the calculator, hit second, vars, go down to normal, CDF. We want to punch in negative 10,000, comma, 1.23, close the parenthesis, hit equals. We get that this area right here is 0.8907. And then all we want to do is take that number and subtract from 1, and that's going to tell us the blue area, the area to the right. You could do the same thing on your chart. Find the 1.23 on here, find that area, subtract it from 1, and that'll tell you the area to the right. Remember, the chart and the calculator is always doing the area to the left. Now do this for me, Grant, on your calculator. Because I think on your guys' calculator, on the new calculators, it makes it easier. Punch in negative 0.75 as your low limit and 1.23 as your high limit. See, I don't think mine will do it. Second vars 2, negative 0.75, comma, 1.23. What'd it come up with?
6.664.
Yeah, so this is a waste of time then. So all you would have to do, if we go back to that calculator, You punch in this number, you punch in this number with a comma in between it with that normal CDF, and it'll tell you that area. Now the bad thing on the chart, if you're using the chart, it won't tell you that. What you'd have to do on the chart is find this area from here down, find this area from here down, and what are you going to do with those two answers to get this area that's in between? What if you knew that this was,
You add them together and subtract them from one, or, and then that's the blue area?
what would you do with this? If this area is 0.89 and this area from here down is 0.34, what would you do with that to get this blue area?
Subtract them from one.
Not subtract them from one, just subtract them from each other to get blue area here. That's if you're using the chart. If you're using the calculator, then you can just put this in as your low limit, that in as your high limit, and it gives you the answer. To make sure we did this right. What'd you say your answer was, Grant? About that?
Missed that. Well, one's a little different,
It's pretty close.
yeah. One's like a million off,
So if we wanted to find this area, we just punch that number, put in negative 10,000 or whatever over here to get the low limit. High limit's that, we can find that blue area right there. You could use, again, you could use the chart to find it. This, if we went to the right, this is why I draw this every time. This time we want this area, so what you could do is use 1.06, come down this way, and it would give it to you. I don't know if the calculators try it, Grant. Let's see if we can, on your calculator, punch in like 10,000 as the high limit. If we do second, vars, normal,
What do you want us to plug in?
1.06, comma, 10,000, close parenthesis, come up like 14%.
I actually got 15. It was around
14. So you could just do that. You punch this in, punch in some way high limit, and it works on the old calculator too, and it'll give you the area to the right. So all this stuff is sort of a waste of time, unless you're using the chart. Come on, come on.
We have homework, don't we?
Sounds like fun. All right, the assignment's on page 244.
Is it online yet?
No. 2 through 8, 10 through 37, 40. We're going to work some of these together, didn't have a chance. 43, 45, and 50.
So we do
No,
the 45 and 50?
45 through 50.
That's it,